This is BBC4 and the Sky at Night with Sir Patrick Moore.
Good evening. In this programme, we're going to talk about the biggest bangs in the universe. First of all, our news notes. Chris, let's begin with the crumbling comet, Schwarzmann-Watson. It's breaking up in front of our eyes.
It certainly is, and the images are spectacular. It first broke up more than a decade ago, but it's really on the way out this time. And in particular, images from NASA's Spitzer Space Observatory in the infrared show a meteor stream, a whole collection of small particles trailing out on either side of the main fragments.
A funeral pyre, in fact.
Absolutely. Now, the Earth is going to intersect that funeral pyre. It's between about May the 19th and June the 19th, so right now, and we might see a few meteors in the shooting stars in the sky. Not too spectacular, but watch out for 2022, when we should get a really nice new meteor storm from Schwarzmann-Watson.
Now let's move further out, shall we? Saturn and Titan.
Yes, now this is an exciting result. We've been talking for months, years, ever since Cassini first got to the system, about these mysterious dark patches on its largest moon, Titan. Now, we hoped they might be seas.
Yes, but they're not.
They're not. They were reduced to lakes, and now it's clear. We've got radar maps of these, and they're deserts. You see sand dunes running for miles. And actually, it looks rather like what you get if you do a radar map of Namibia. It's just a large sandy desert.
Rather disappointing, I think, in many ways.
Yes.
Well, back further now, Mars. Mars Express going around and showing amazing pictures. Lava tubes on pavement monds.
Oh, they're spectacular images. And of course, because it's Mars Express, we have a 3D view. And we can get down and look at a perspective view of these amazing features.
Now, much further out, the Sun's termination shock, where the Sun ceased to be dominant. Both the Voyager probe, which bypassed the giant planets, they're going out of the solar system in opposite directions. And they're not reaching the termination shock when we expected.
Voyager 2 has encountered the termination shock, the edge of the solar system, about 1 billion miles before it should have done. So that's telling us something about the way the Sun's influence, its magnetic sphere, interacts with the surrounding environment.
Our own solar system is fascinating, but others too. One star has been found with 3 Neptune-sized planets.
This is a result from the European Southern Observatory down in Chile, an amazing instrument that can detect the wobbles in stellar motions very precisely, just a few kilometres per second. And in this case, it's revealed a trio of planets. One orbits its star in about 8.5 days, one in 30 or so days, and one is something like almost 200 days. They're all Neptune-sized. They're between 10 and 18 Earth masses. Those are minimum masses, but even so.
Of course, if there are big planets there may be small ones too.
That's right, and the exciting thing particularly is that the furthest out of these planets, which is Neptune-sized, is just on the edge of the habitable zone. So it's probably got some ice, some liquid water, and as well as a thick atmosphere.
And of course, if it's giant, it may have satellites.
And they could be potentially Earth-like worlds. So we're narrowing in all the time on places where we might find worlds like our own.
Well, let's go further out now, shall we? Your own particular topic, Chris, gravitational lensing.
Yes, this is just a fantastic image. What's happening here is a galaxy cluster is bending the light from objects behind it. So rather than just seeing one copy of this quasar, like looking through a funfair mirror, we see 5 different images of the same distant object. And it's beautiful, but it's also useful. We can use images like this to weigh the galaxy cluster and tell us about the distribution of mass in this large object.
There's so much we're finding out now. Infrared, this new Japanese satellite, Akari, going to survey the sky at infrared wavelengths.
Yes, and it's a Japanese satellite with Korean and European involvement. And I talked to one of the scientists who's waiting to use it.
Well, the wonderful thing about Akari is it has wonderful sensitivity, so we can go really deep in space, and also the resolution. And the third thing about it is its wavelength coverage. So we have satellites like Spitzer that are currently flying an infrared space telescope, but the problem with Spitzer is it only starts recording around 5 microns, and it's going up to around 200 microns. This satellite, it's really the depth of its wavelength coverage and really the uniqueness of its sky coverage that's really going to benefit the astronomy.
So we've already got the first images. For example, these images of M81, a nearby star-forming galaxy, show everything from the active nucleus in the core, material around the black hole, through to the star-forming regions in the spiral arms. And then we've also got this image of a star-forming region in our galaxy, and you can see the different wavelengths and the different features they reveal. But Akari is not just an imaging mission. It'll do spectroscopy as well.
Absolutely, that's my key area of interest. I'm really interested in using not just the imaging cameras, but really trying to look at the spectroscopic features, what we're going to see happening with the molecules, how they're moving, where they're at, what they're doing. Its resolution as a spectrometer probably isn't quite as good actually as some of the infrared satellites that have flown recently or are flying right now, and certainly not as good as the resolution we can get from the ground. But the very important thing is we actually cover a range of wavelengths we can't see from the ground, and so it gives us some really unique information that we haven't had a handle on probably since ISO, the European satellite, flew in the late 1990s.
So what sort of molecules and why are they important?
Okay, so the kind of molecules I'm going to be looking at are actually what we call solid molecules, or ices. So in space, especially in the regions of star formation, we have gas and dust. And what we're interested in is we're interested in understanding how the gas and dust interact with the atoms and molecules around it. And molecules, basically, when we have molecules present, they enable the clouds where stars are forming to cool, and they have a very pivotal role to play in the star formation and planet formation process.
And we're talking about everyday molecules like water or...
Absolutely. Water is the most abundant molecule we find in the solid state in space. In fact, we have ice everywhere. Unfortunately, it's not like the kind of ice we find in our drinks in the evening or that we can go skiing on, but it is a very interesting kind of ice. It's very fluffy, and if you imagine a bath sponge, it's a little bit like that, got lots of holes in it. And so it has the properties that we're able to sort of trap other molecules like carbon monoxide and carbon dioxide inside it and do a whole bunch of additional chemistry which generates sort of more complex molecules, which we then can see with these satellites once again at longer wavelengths.
Well, it's an exciting mission. Come back and tell us when you have some results.
Thank you.
And now, on to our main programme. Gamma-ray bursters, the biggest bangs since the Big Bang. And I'm joined by Dr Nial Tanvir, University of Hertfordshire, and Dr Julian Osborne, University of Leicester. Welcome to the Sky at Night. Julian, can I come first to you? There are two definite types of burster, are there not?
Yes, it was known for some time that there were both long and short bursts, but in fact both types of bursts are really very fast. A typical gamma-ray burst would be a few seconds long. The short bursts are shorter than 2 seconds, and the long bursts are somewhat longer than that, maybe up to 100 seconds long.
How do you detect them?
The origin of the gamma rays is measured by a shadow camera. We work out the position by the position of a shadow. So just like my hand in front of my shirt here tells you that there's a spotlight in front of me, if you have a source of gamma rays illuminating a grid of opaque tiles in front of a detector, you can work out where the source of the gamma ray was with respect to the position of the satellite and the pointing of the satellite.
What about the Swift satellite?
Well, the Swift satellite is something that I'm very closely involved with. It was launched in late 2004, and we've now had our first year of operations. And Swift has a very sensitive gamma-ray burst telescope on board, and it also has sensitive optical UV and X-ray telescopes. And this makes it a very powerful tool for investigating gamma-ray bursts.
Now, what causes them?
This has been the $6 million question for many years, and we have made a lot of progress in understanding what causes gamma-ray bursts, but there are still a lot of mysteries to solve, and so I'll tell you what we know. Certainly it seems that the bulk of gamma-ray bursts that we're looking at are occurring due to the death of a particular kind of massive star. Now, we don't actually know exactly what kind of star this is. We know it must be a rare kind of star, and we know something about its properties. It's certainly got to be a massive star, probably rotating very fast, and one which, when it reaches the end of its life, it runs out of its fuel, it collapses like a normal core collapse supernova event, but in this case we believe that it's creating a black hole instead of a neutron star at its centre, and it's the energy of the material falling into the black hole that somehow is tapped when a gamma ray burst goes off, and that energy, it seems, shoots out in jets either side of the forming black hole. And if we happen to be looking straight down one of these jets, because the jet is coming at such remarkable velocities towards us, we see the flash of gamma rays that it produces.
They are a long way away, are they not?
More than halfway across the observable universe, typically. And so they have to be incredibly bright, of course, for us to see them as bright flashes as we do, even in the Milky Way.
How often do they occur?
Well, with SWIFT, we detect a burst every few days. Over the last year, we saw about 100, so once every 2 or 3 days. Of course, because, as Niall says, they're jetted, there are many bursts going off which the jets are not pointing towards the Earth, and so we don't see them. And so the true rate of gamma ray bursts in the universe is quite uncertain, because we don't know how broad this jet is.
It was once thought they were due to a collision between neutron stars. That theory is out now, is it?
Well, that theory certainly doesn't explain the long gamma ray bursts. As Niall was saying, that's probably associated with a supernova type explosion. But for the short bursts, a collision between two neutron stars does seem like quite a likely idea. SWIFT detected a number of short gamma ray bursts in its first year, and crucially, for the first time, we saw the fading afterglow of a short gamma ray burst. And that allowed people to use large optical telescopes to measure the redshift, which tells us the distance to these things. And it also told us where they were in respect of their host galaxies. And we saw that short gamma ray bursts are occurring in a very different sort of galaxy to the long gamma ray bursts.
We're talking about immense power. How immense?
There are a number of different ways of expressing the power. One would be to say that the gamma ray bursts at their peak power are perhaps tens of thousands of times brighter than any other objects that we see in the universe, so quasars, which are otherwise what are regarded as the very most luminous objects that we see. GRBs, just for the moment that they're at their brightest, are, like I say, tens of thousands of times brighter. Another way of looking at it is, since Einstein, we've known that we can consider energy as an equivalent to a certain amount of mass, and so the very brightest gamma ray bursts we've seen appear as if they've converted a substantial part of, let's say, the mass of the whole sun into energy in just a few seconds. So that's the kind of immense energies that we're talking about.
It makes a supernova look pretty feeble, doesn't it?
Yes, the brightest gamma ray bursts are probably quite a bit more energetic than a typical supernova. And, you know, because we're seeing such distant objects, they need to be very bright for us to be able to see them, of course. Whereas a supernova probably gives off light and energy in every direction equally. For gamma ray bursts, because we're seeing this very strong jet, we don't know what the true energy of these things is, I would say, you know, within some uncertainty, because we're just looking down this special direction of the jet.
Before we come back to you to talk further about this, what about supernovae? Well, Chris has been over with Tom Boles, the supernova hunter.
Few people realise that one of the world's most productive observatories is in a Suffolk garden. Over the last 10 years, Tom Boles has used a set of robotic telescopes to search for supernovae. When he started just a decade ago, not a single supernova had been discovered from the UK. Yet just a few months ago, he found his 100th, a unique achievement. His 3 telescopes moved rapidly from galaxy to galaxy throughout the night, sending images to a control room inside the house. We're hoping to be lucky tonight, but although the sky is mostly clear, there's a lot of high cirrus cloud to contend with. So Tom, how did you get started in all of this?
Well, astronomy in general, I've been interested in astronomy for a long time, but the specific reason why I chose supernova is that they're not too challenging as far as the quality of sky is concerned. It's not like a photometry where you need sort of very pristine skies to do your measurements. So that was the attraction of doing supernova.
So you started in October 1996, and it took a while to get your first supernova.
It took about 12 months to get the first one. People often ask me, what does it feel like to discover your first supernova? Now, the answer they expect is, you know, it's a marvellous feeling. You see this thing come up on the monitor. You're the first person perhaps in the galaxy to see this supernova. And I tell you, it's absolutely nothing like that. Your heart starts to beat. You become terrified, you know. And you say, you've been looking for this thing for a year and you've suddenly found it. And you say, what do I do now? Who do I tell? How do I check? to make sure this is actually a real supernova. So the way they proved that a supernova was real was they got a large telescope somewhere to go and take a spectrogram of it. And of course, something like a 1.5 metre telescope sort of goes off its work for the night and goes to take a spectrogram of your discovery. Then it turns out to be false. So that was the worry. And it took nearly 3 days to get it confirmed, and it was quite a stressful time. So yeah, I can remember that one very, very clearly, believe me.
And the question I can ask you and no one else in the world is, how does it feel to discover your 100th supernova?
You enjoy it a little bit more because you've got sort of 10 years of experience, so the terror goes away from discovering it, and you've got routine checks to do. And it's a nice supernova. It's a Type 1a, it's quite bright. I would have preferred the galaxy to have been a little bit prettier than an elliptical galaxy, but then you can't choose.
No, you're getting picky now.
You're getting picky now. Yeah. But it was nice, and just the thought of getting the 100th was quite good, because the whole thing about this, if it wasn't enjoyable, I wouldn't do it. And the motivation comes from loads of different places. You see these lesser known galaxies, the ones that are not imaged so often, coming around year after year, and you start to associate with them. You don't remember the names, of course, but you can remember the shapes and the structure, and you see it's the old friends coming around each year.
And some of them old friends that had supernovae in the past.
Indeed, yeah. And as soon as one of your own come up, of course, the little bell rings. I remember that one. That's one of mine,
So what's the plan for tonight?
Well, the plan for tonight's a full moon tonight, which isn't ideal again.
It's just rising over there.
Just rising over there. So what we'll need to do is we'll start off in the evening sort of patrolling west of the moon and keeping to about sort of 15, 20 degrees away from the moon on the west side. And then once the moon passes the meridian, we'll swap all the telescopes over and we'll look at the eastern horizon and start to patrol down that area.
Well, let's hope it's clear.
Right, we'll do.
A typical supernova marks the death of a massive star. Deep within its core, nuclear reactions produce first helium and then more and more massive elements. Iron is the most stable of all atomic nuclei, and when it appears in the core, the chain stops. The source of energy for the star is turned off. The star implodes and then quickly rebounds in a massive explosion which we see as a Type 2 supernova. Type 1a supernovae are much rarer. They occur in binary systems in which a massive star is orbiting a white dwarf, the last faint remnant of a sun-like star. Material builds up on the surface of the white dwarf until a critical density is reached and nuclear reactions can ignite. The resulting flare can easily outshine the entire galaxy, and that is what Tom's telescopes will be looking for tonight. With the night's observations underway, Tom's already able to analyse the first few images of galaxies. Well, the telescopes have been running about an hour now. There are live images coming in. Here's the latest of them. But we can actually start comparing these images to the masters, I guess.
Indeed, that's what we're doing here. This is NGC 4319, and we've aligned the two images automatically in the software, and we've started to blink them. So the idea of blinking them makes it very, very easy to see changes. Just as we expected tonight with the full moon, the image quality is slightly deteriorated.
But I can't see any supernovae. There's
not any supernova on that one. So let's have a look at the next one, shall we?
Okay, yep, let's work our way down.
That's NGC 4133. You can see the name down there, and there's a little bright thing in there sitting on the... That's a potential supernova, so what we need to do is we need to dim the template down a little bit, and let's just see if it's sitting in the template as well.
Oh, it's very difficult.
It's coming, look. Yep, and it's on the template.
Yeah, there we are. So it is there.
It is there.
First false alarm of the evening.
Yeah, well, it'd be too much to hope for something this early in the evening, isn't it?
Magic of television.
Yes.
What would an actual supernova look like when you blink it like that?
Here's an image of the 100th supernova. It's in a galaxy MCG 63320. Here's the galaxy itself, in a little elliptical galaxy, and the star you see to the left here blinking on and off, that is a supernova.
Well, that's reasonably obvious. Was this a typical one?
That's relatively bright as a supernova goes. It was a Type 1a, and the galaxy, although it's reasonably distant, it's pretty easy to spot.
And of course, some are more interesting than others. There have been a couple of really, really interesting ones.
Yes, I think 2003L was a very important supernova for me. It was a very bright, high energetic one. In fact, it was the second most energetic supernova of all time. And there's a very loose connection between that and a gamma ray burst that happened in December 2002. So there's a link there between the two phenomena.
I mean, we think that long duration gamma ray bursts are essentially just massive supernovae, supernovae, I guess.
Yes, I think any gamma ray burst that lasts anything longer than, say, 100 seconds we categorise as a long gamma ray burst. And the ones that we have discovered and we have managed to get optical counterparts to have nearly always turned out to be a type 1c supernova, so there is a very strong connection there. And if we look at supernova AJ, which has been studied for the last year or so, that was one of the longest gamma ray bursts ever. I think it was 2,000 seconds it lasted for. So the whole science is starting to sort of solidify around the sort of the theory that every gamma ray burst is associated with some kind of core collapse event supernova.
So 2:30 in the morning, and we've been running for a few hours now. How's it going?
The sky is starting to deteriorate, as you can see. The mist is starting to form. There's high cirrus cloud, and it's been illuminated by the moon, and it's showing up all the faults in the
So
chip now.
just this light background.
Just light background. So we've lost our depth of magnitude quite severely. We're really at the stage now. It's time, I think, to put the temperature off in the cameras and park the telescopes for tonight, unfortunately.
Well, supernovae for somebody else tonight. But
Possibly.
there's something we should say is that amateurs have a huge advantage over professionals for this kind of work.
Very much so. I mean, if you think it takes 3,300 images to find a single supernova, amateurs can use relatively inexpensive telescopes to search a large number of galaxies. So there's no way professionals could do this in an economic way. It would be a waste of large telescope time, basically.
And yet you can produce results that are incredibly useful for professionals to follow up using the large telescopes.
Indeed, that's what they do. I do the donkey work of finding the supernova. They pick up the discovery and they go and do the analysis and do the research on it. I mean, just about every major telescope in the world has followed up on my supernova, the Hubble Space Telescope, the two big Kecks. And it's very nice to do a report saying that Keck 1, Keck 2 followed up on your supernova. So it gives me quite a buzz.
Even after a decade of doing this?
Even after a decade of doing it, yes.
Well, for once, I'll let you get some sleep this evening. Thanks very much.
Thank you, Chris.
There are certainly larger teams with more expensive equipment chasing supernovae, but few have been more successful than Tom's 100 discoveries to date. There's plenty more to come, and I look forward to reporting on his 200th in a few years' time.
Well, supernovae seen in other galaxies, and one even in the Large Magellanic Cloud, only about 170,000 light years away, but none nearer than that. And if we had a gamma ray burster in our galaxy, it might be very dangerous.
It could be very dangerous indeed. Supernovae, of course, can be dangerous if they were to go off near the Earth, but a gamma ray burst is that much more powerful that we believe it could be detrimental to life on Earth, perhaps even exterminate life on Earth, even if it were as far away as, let's say, a few thousand light years away from us. What we've discovered, though, which gives us some degree of comfort, is that the kinds of galaxies gamma ray bursts are taking place in seem to be, generally speaking, rather different from the Milky Way.
What kinds of galaxies are these?
They seem to be rather smaller galaxies than the Milky Way, perhaps a bit more like the Large Magellanic Cloud, in fact, and the Small Magellanic Cloud. Small galaxies where, in particular, the chemical enrichment is a lot less than it is in the Milky Way. The Milky Way has been forming stars for so many billions of years that those stars have cooked up heavier elements and spread those out throughout the gas in the galaxy. And most of the stars, at any rate, within the Milky Way are therefore sort of enriched in heavier elements. In some of these small galaxies, particularly in the early universe where we see a lot of these gamma ray bursts, much less enrichment had taken place. The stars were of a rather different kind, therefore, nearly all just hydrogen and helium. And it seems that those conditions favoured the production of gamma ray bursts much more than the present day conditions in the Milky Way. So we're hoping we're safe.
The old theory of colliding neutron stars doesn't explain the long burst gamma rays, but what about short bursts?
The short bursts are probably due to colliding neutron stars. That is what we think is the most common origin for these. You know, you might ask, well, how can two neutron stars collide? They're only 10 kilometers across. The chances must be very low. But what we think is that they're in a binary orbit around each other, and that orbit shrinks slowly because of the emission of gravitational radiation, and it shrinks to the point where the two neutron stars actually touch. They actually do collide, and this raises immense tidal forces which heat the neutron star, and you get a kind of rotating collision which in some way, which we don't understand, produces a jet with these immense velocities which we see as a gamma ray burst. It's also possible that a neutron star could collide with a black hole or even a white dwarf.
Are there any other theories apart from this? Collapsing giant stars or colliding neutron stars?
Over the years, there have been a very great number of theories which have been proposed for gamma ray bursts, and one of the nice things in the last decade or so is that we've been able to rule out so many of those. But interestingly, there's been one new one that has only really come into prominence, I would say, in the last year and a half, which is that some neutron stars within our own galaxy seem to have very immense magnetic fields. It seems that they've got magnetic fields which have been sort of wound up like a spring till there's a huge amount of energy just stored in the magnetic field of the neutron star.
Magnetars, in fact.
Magnetars, exactly right. And it seems those fields can in some circumstances kind of snap. And when they do, a lot of this energy that was stored in them is released, and that itself, it seems, can produce an event like a gamma ray burst. And we've seen one very clear example of that, and the suspicion is, and there's some good evidence to back this up, that in fact a fair proportion of the short duration gamma ray bursts that have been previously observed are actually due to that kind of event instead, taking place much nearer by within the universe, within galaxies that are perhaps a few million light years away from us, rather than in the very distant universe like the bulk of the gamma ray bursts.
There is one other theory for the origin of the bursts, and that is accretion-induced collapse of a neutron star.
Oh, yes.
So if you have a neutron star which is accreting material from a binary companion in a close orbit, then this accretion can continue and continue until it pushes the neutron star over its maximum mass limit, probably not much more than 3 solar masses. And if that were to occur, then the neutron star would collapse to a black hole. And very recently, people have been proposing that some of the gamma ray bursts might be due to this.
But a neutron star is only a few miles across. Surely it can produce as much energy as a gamma ray burst.
You're quite right, they're extremely small, 10 kilometers across, that sort of size. The energy densities are immense. I mean, the energies, everything about gamma ray bursts is utterly extraordinary. I mean, you know, they convert a substantial fraction of the rest mass of the sun into energy in a few seconds. The energy densities are extraordinary. The velocities of the explosion that we see are 99.999% the speed of light. Everything about them is just amazing.
Then, what do you think are going to be the next major developments in gamma ray research?
One thing that SWIFT has done that previous satellites didn't do is find gamma ray bursts at really very, very great distances, right back into the very earliest times of star formation in the universe. What we're hoping is that, although even with SWIFT these are rare events, we're hoping to build up numbers of them so that we may eventually find a gamma ray burst which is further away than any other galaxy or quasar that we've ever seen, and that way use the gamma ray burst to tell us about the very early universe, the time when the very first stars and galaxies were turning on.
What's the distance record so far?
The distance record for gamma ray bursts is a redshift of 6.3. Now, in terms of time in the universe, that means that it was taking place about 1 billion years after the Big Bang, slightly less. And that's very close to the record redshift for the most distant galaxies as well, which are just very slightly further than that. So the hope is that within the next year or two, if we can be fast enough and follow up all of these gamma ray bursts that SWIFT is finding, we'll find maybe 1 or 2, perhaps even earlier, maybe a few hundred million years after the Big Bang.
Niall, Julian, thank you so much. SWIFT has much to tell us. Next month we'll come much nearer home and talk about the origin of the planets and how the gas giants like Jupiter have affected us. Until then, good night.
The Samuel Johnson Prize for Non-Fiction is back. Find out all about the contenders and their books on Wednesday at 8:30. Tonight, the pioneering family who made a North Yorkshire town the unlikely home of a booming film empire way back in the late 19th century. Holmfirth, Hollywood, next.